This video will be a practice problem of a multi-component flash distillation. It says a flash chamber operating at 50 C and 200 kilopascals separates a feed that is 30% propane, 10% N-butane, 15% N-pentane, and 45% N-hexane. Find the product composition and flows. First thing to do is to draw yourself a process flow diagram. I recommend that you pause the video now and try to get as far as you can with this practice problem without seeing the solution. Okay, here's my diagram, and as I was drawing the diagram, I realized that I've got some poor question writing practices going on here. So what I was noticing is that I did not give you a basis, and yet I'm asking you to calculate the flows. So I'm going to amend this problem statement, and I can do this now because this is my video, and I get to choose which problem we do. And we are going to say, assuming a basis of 100 moles per hour. I hope that didn't sound pompous. That was mostly a joke. Of 100 moles per hour. All right, but the point is that if I'm asked to calculate what the flow rate is, then I must know what the basis is. Because if I choose a different basis, then obviously I will get a different answer for my flow rates. All right, so I can do a degree of freedom analysis here and find 9 unknowns. But we do have T and P, so therefore we know what the equilibrium values would be for each one of those. We also have material balances that we can do. Sorry, did I say 9 unknowns? I meant 10 unknowns, VL, and all the compositions. So my degree of freedom analysis technically would be 10 unknowns minus 4 material balances minus 4 phase equilibrium relationships minus 2 physical constraints because I counted each one of the 4 compositions as unknowns. So option 1, if this were my material and energy balances class, would be to write all 10 of those equations and then solve those 10 equations for 10 unknowns. Or what we can do in separations is use the tools that were given with the de Priester chart and the Ratchford-Rice equation. So what I'm going to do is label my de Priester chart with the information that I know. So I know that my pressure is 200 kilopascals and my temperature is 50 kilopascals. And I'm going to connect those with a line. All right, so in order to read this thing, we are going to have to break out our magnifying glass. And actually, paradoxically, I think the closer you zoom in, the more difficult it gets to read. So I'm going to try and zoom out a little bit, maybe. I mean, if this helps you, you can pause the video now, but I'm going to zoom out a little bit. And yeah, I think that's actually a little bit easier for me to read. So my K values. K for propane is going to be this line. And I am 90% sure that that says 7. K for butane is going to be on this line. And that is going to be between the 2 and the 3. And I think it's 1 tick mark below the 2.5. So I'm going to say that is 2.4. Right, this little tick mark right there is the 2.5. Pretty sure. Oops. Yeah, I'm not going to try and erase that. I'm just going to leave it. Let's see, what's next? Pentane, KPE, is going to be this line. And let's see, I'm on this one, 0.8. Okay, so notice that already my constraint is satisfied. I have K propane that is greater than 1 and a K pentane, which is less than 1 at 0.8. So my constraint is satisfied without even having to look up what hexane is, but I do need hexane in order to proceed. Hexane is going to be 0.3. And another context clue that you can use is that the longer the hydrocarbon chain, the less the value of K should be. And that reflects the fact that, again, K is equal to Y over X. And the lesser this value is, then the lesser the vapor phase composition is going to be in relation to the liquid phase composition. All right, so now that we have these K values, we can now plug them into the Ratchford-Rice equation. So that is the next part. All right, and I, again, recommend that you go through the derivation of the Ratchford-Rice a few times because you can use it in this specific situation, but again, think about what would happen if something were to happen and you could not automatically apply this Ratchford-Rice equation. Okay, my Ratchford-Rice got a little bit too long to fit onto one line, so I just made it onto 2 lines. And notice that we have everything in this equation, except we do not know what the ratio V over F is. V is our only unknown in this equation. Everything else I can plug in to solve. So given that, try to think about what strategy would you use now to solve for V over F. I don't think you're going to want to algebraically rearrange this. So this seems like the perfect problem in which to use one of my favorite tools. I think my OneNote just froze. Okay, sorry about that slight technical difficulty. Had to reboot my tablet, but I'm back now. I was saying right before that goal seek would be the way that I would elect to solve this problem. So there's one single unknown, which is V over F, that I want to solve. I know everything else. Let's go ahead and plug everything else in. Z propane is 0.30. K propane minus 1 is going to be 6. Z for butane is 0.10. And KB minus 1 is 1.4. Pentane is going to be 0.15, and K-pentane is negative 0.2 because it's 0.8 minus 1. So this is where we're getting our negative term now, minus 0.2. And notice now that we're multiplying this 0.2 by a fraction that is between 0 and 1, and then adding 1. So again, the denominator is going to end up being positive. And Z-hexane is 0.45. K-hexane is 0.3, so this is going to be minus 0.7. So in order to solve this, I'm going to plug this into Excel, like I said. I'm going to goal seek using V over F as my unknown, and I will report back what I find. Okay, so I did this. I remember I wrote this problem once upon a time to make it such that the answer that I got was close to 0.5, but the V over F that I got is 0.511. Now, I want to make a point here that the answer that you get for V over F is extremely sensitive to the values that you get from reading this DePriester chart. In other words, if I had, instead of reading 0.8 was my K for pentane, right? If instead I had said, well, that's 0.7 or maybe 0.75, I might get a different answer here. So when you're reporting this V over F, kind of doesn't make a lot of sense to report to a lot of significant figures, just because, like I said, you should try it with the different values for these Ks, and you'll see how different your V over F should be. It should be in the right ballpark, though, so it's not going to change by too much, but it can change considerably depending on the values that you get for your Ks. Now that V over F is solved, I can now plug that in, and I can solve for V and L. So V over F is 0.511 and F is 100 moles. Then V is going to be 51.1 moles per hour. And L is going to be 48.9 moles per hour. And now what I can do is plug back in for my X values. So I can write formulas now. I derived this expression for X of I in the last video. Xi is equal to Zi divided by V over F times Ki minus 1 plus 1. So for each one of the components, you can then calculate what that X is and then simply multiply it by K in order to get your Y. So Y is equal to Ki times Xi. So I'll just do a couple of examples. So for propane, for example, X propane is going to be 0.3 divided by 0.511 times 6 and plus 1. Performing that calculation gets me that X propane is 0.074. So 7% propane, which is going to make sense, right? Propane is the most volatile component. Therefore, I would expect that the liquid phase composition of propane is very little. My vapor phase composition of propane should be much greater. So I'm going to multiply that times the K value, which we decided was 7. Oops, I put the wrong number on my calculator. Times 7. So Y propane is equal to 0.516, which is making sense. It should also have the constraint, remember, that the Z for the component should be in between what your X and your Y is. That's the only way the material balance can work out. So here we've got Z is 30%. My Y propane was 51.1%. Was that what it was? 51.6%. No, it's 51.1 moles. 51.6%, and propane in the liquid was 7.4%. And you could do that similar calculation for each of the other three components. I won't bore you with the details and show you how to do all of those. The one last thing that I'll mention is that the fractions or the percentages should all sum up to 1, but they probably won't be exactly 1. And that is because, again, you have some error when you're reading this de-Priester chart and how the precision level that you can get your K values. So don't get too caught up in trying to be too precise reading this graph. For the purposes of this class, if you're close enough, that is going to be close enough to just be aware of. You may get some disagreement, especially sometimes these problems can be over-constrained by reading that chart. You won't be able to get complete closure to the degree of precision that you would expect. So that'll be all for this video. I'll see you in the next class.